Hello friends, I came to you with yet another new topic which is offset slider crank chain. So it is offset slider crank chain. So we know about inline slider crank chain, right? We have seen all the inversions of inline slider crank chain in the previous videos. But then what is this offset slider crank chain? Just look at this. I'll just explain and then you will understand. Fine. So inline slider crank chain is a slider crank chain where you can see that the axis of the slider as well as the center of rotation of crank both are in the same line. Fine, but here what is going to happen is a little different thing. So this is our red link. Fine, this is our crank. So crank is going to be at a certain distance. It is not going to lie in the same line, but the center of rotation of crank is going to lie at some distance from the slider, a line of stroke of the slider. So you can see this, right? So this is the line of stroke of slider. Fine, let me draw some position in the middle over here, right? And let's draw the slider. This is our slider. Now, so this is the center of rotation. This is fixed and even slide. So this entire thing is a single link. I hope you understand what I'm saying. You can say that entire thing is a single link by just connecting it this way also. Yeah, entire thing is a single link. I hope you're understanding. You can see very clearly, right? I'm just removing this because it's a frame. Fine. This entire thing is a single link and it's fixed nicely. And this is a revolute over here. And this is a revolute over here. And this is a revolute over here. So 3 revolute and 1 sliding pair. Okay, 1P. So I can say here again 3R 1P. So first case what we did do 4 R's. Then that 4 we have changed it into 1P. Instead of 4 revolute pairs, we thought that according to our equation, mobility equation, if we want a mobility equal to 1 or degrees of freedom equal to 1, what did we do? We said that we needed 4 lower pairs. So in 4 lower pairs, we could do all revolute joints, or you can make a combination of prismatic and revolute. Fine. So this was the case. So now the question is, at what distance from the axis of this slider is the center of rotation placed? Okay, we'll clear all those doubts. I am going to give the distance right away. We are going to say that it is offset at so and so distance. We are going to say that it is offset at such and such distance. Okay, from the line of stroke. Let's say this is the line of stroke. Yes, it is the line of stroke. Okay, from the center of the slider, if you trace the path, okay, you will get the line of stroke, and this is the center of rotation of your crank. Fine, and this is given an alphabet E, offset E. Fine. So now we are going to write, this is the link number 1. Okay, link number 1 and link number 2 here, link number 3 and link number 4. So now we are going to check for the extreme positions. How is it different? How is it different from our previous slider crank chain? If it is inline, what is the problem? And if it is offset, what is the issue? Okay, why are we studying this in a different manner? Okay, then we have to draw the extreme positions, right? Usually we always draw the extreme positions, right? So now for extreme positions, we have to take the same diagram, right? And then this is, let's say that, okay, sorry. First, let's trace the position or the circle of our rotation, right? Rotation of the crank. Crank is link number 4. So let's say that the crank is rotating. Okay, the center. 1 second. Give me some time so that we properly can visualize each and everything, right? Yes, yeah, yes, almost fine. Okay, for our convenience, I have done it little bit. Yeah. Right. So this is the path traced by the crank, right? Path traced by the crank. You can see clearly. Now for extreme position, what we need to do? We have to make it such that it is inline, right? It is in a single line. It means 4 and 3 will be in the same line for extreme position. So let's take the link pink one, and actually it is not entirely pink, but I'm drawing in this way so that we won't have any confusions. Okay, so here now I'm going to draw the red one also. Yes, so this is the red link, right? Yes, this is the crank over here, and connecting rod is there, and they are in line. So this is the first extreme position which we could easily draw, right? Yeah, and now let me draw a slider also to complete the picture. So this is the new position of the slider, like 2 dash position. Fine. And then next we wish to draw. See, this is the first extreme position. It means the crank came to this position rotating anti-clockwise. For example, it is rotating anti-clockwise. So the crank came to the inner dead center. Okay, the crank came to the inner dead center. Fine. And now the crank still is rotating anti-clockwise, right? So we are imagining the crank is rotating anti-clockwise. And then we have another new position, right? Another extreme position. Yes or no? Yes. So let me draw the another extreme position. I see that the crank is coming to this corner, right? So the crank is still rotating, still rotating, still rotating. Fine. The crank is nicely rotating. Let me adjust it properly so that it will help you in visualization. Fine. I hope you can see the crank. The crank has taken the connecting rod to the other side. Actually, the crank is under it. Just imagine the crank is under the pink link on the other side. Fine. The crank is taking the connecting rod to the other side. Let me draw the connecting rod also. So the connecting rod is taking the crank, and let me draw a little bit far. Okay, little bit far, so that you can see both the things. They are overlapping one upon each other. Fine. And now you draw the slider. So this is your slider, right? This is your slider and new position of the slider. Fine. Now I am going to give all the labelings and everything. And let me take a good color and see. This is a revolute pair here. This here you already have a revolute pair. Here one is revolute pair. Here revolute pair, and here revolute pair, and a sliding pairs. Let's say that from this position, to this position, as the crank is coming, and as the crank is moving, okay, from this position to this position, this is the forward stroke, right? Because see, combustion is happening here, then it's going forward stroke. Fine, backwards. And then this is your return stroke. The distance traveled, is it different here on the slider? No, distance traveled is same. Forward, return, stroke length is same. Fine. And how do you find out the stroke length? We'll see now, right now. Okay, how do you find out the stroke length? Just we'll first complete it. So this is your R, right? Radius, and this is your L. Now what is the and if you look here, if I just connect this, we'll connect this. Okay, let's say that you can see easily that this is a right angle triangle, right? Over here, this is E length in the height, and you can see that, let's say this O A B, right? O A B, and let's say this point is K. Fine, this end. So I can say that okay, and let's say this point as G. Fine. Now to find out stroke length, what do I need to do? Stroke length is BG, right? Stroke length. Okay, let's use the board clearly. Stroke length is equal to BG, right? So what is BG? BG is equal to BK minus GK. Just look at the diagram, BK minus GK. Fine. Little geometry is involved. Kindly bear and slowly you understand. You'll clearly get to know. Okay. What is BG? BG is stroke length, and BG is BK minus BG. What is BK? I can see a right angle triangle here. What is BK? So BK is the adjacent side, and BO is the hypotenuse. So I can say from triangle, I can see clearly a right angle triangle. Okay. And the right angle triangle is what? O, B, and K. So from this right angle triangle, what can I write? I can write that BK is adjacent side, right? So, okay, BO square, use the Pythagoras theorem, BK square plus OK square. Fine. Okay, right? OK square. So, OB square is actually OB is L plus R, right? Because L is the pink length and R is the crank length. So L plus R whole square is equal to what is BK? BK is the thing which we want to find out. So BK square, keep it as it is, plus OK square. What is OK? OK is the offset, which is E square. So now did I get what is BK? BK is equal to under root of L plus R whole square minus E square. It's minus, okay? It's minus, not plus. Okay, E square. So this is the BK square which you wanted. Let's put it in a box so that it doesn't run away anywhere. Okay, yeah. Now the next thing, I want to find out GK square. Now how do I find out GK square? Is it possible to find out GK square? Yes, it is possible to find out GK square. How do I find out the GK square? I can see another right angle triangle, right? Such a coincidence, right? We are continuously finding all right angle triangles. So what is the right angle triangle? From triangle, I'll write away here KOG. Can you see KOG? KOG. See, O is here, G is here, K is here, right angle triangle. Okay, now from this, what can I write? I can write GO square is equal to GK square, hypotenuse square is equal to adjacent plus opposite, E square. Right away, I'm writing OK square is E square. Okay, now what is GK? Sorry, what is GO? GO is total length is L, right? Because pink is total, pink has come over that side. Now red is overlapping, red is R. So can I write OG is total L minus R? Yes. So L minus R. If you are confused, just pause it and think about it. What is OG? Fine. Total is pink length. Pink is L and red is overlapping. So I know this length is R. So it is L minus R. And GK is what we need to find out, right? GK square plus E square. Now what is GK? GK is equal to L minus R whole square minus E square. Fine. So now did we get the stroke length? Did we get it? Not yet, but almost. Almost we got it, right? What is stroke length now? I can see, okay, we didn't put under root. Fine. I'm sorry. We have to put under root because, yeah, you know why, right? So now here, do we have the complete thing? I'm just going to do it here itself. So what is stroke length? Stroke length is BG, right? BG is equal to BK minus GK. So what is BK? BK is from equation 1, GK is from equation 2. I can write down that stroke length, let me write stroke length SL is equal to BK, which is under root of L plus R square whole square minus E square under root minus, because minus sign is there clearly there, under root of L minus R whole square minus E square. So I think if the offset length is given, if the length of the connecting rod is given, if the radius of the crank is given, immediately look, you can write down, you can remember the formula under root of L square plus R square minus E square minus under root of L square minus R square minus, is it L square plus R square minus E square minus under root of L square, sorry, L minus R whole square minus E square. Okay, while I'm telling, if I made a mistake, I'm sorry for it. Okay, it was in a hurry, but I think clearly you can see here what I was trying to tell, right? Under root of L plus R whole square minus E square minus under root of L minus R whole square minus E square. So this is stroke length. Okay, well and good. Is the stroke length sufficient right now? Is it the end of the offset slider crank? If it is sufficient, then why are we using this? Because slider crank, if you check here, now we are going to get into details. Now, as OA goes to OA dash, this is A dash, new position of A. See, look at this. This crank, if it is rotating at constant angular velocity. See, suppose we put a motor here. Fine. If it is rotating with constant angular velocity, fine. So, let me use white so that it will look better. So, the angle turned from OA to OA dash, this angle, fine. I'm going to remove it again. I'm going to write here, right? When the angle is turned from OA to OA dash at the same time, at the same time, you can see that B is coming to G, right? See, it is pulling B to G at when it's turning anti-clockwise, right, from here to here. B is coming to G, or B is moving to G, fine, in the linear manner. And then here, what's happening is the angle turned is, you can see that there is some difference, right? See, from here, while it's going from OA dash to OA, you can see that the angle, it is coming from B to G. It means from this corner, it's again going to that corner, right? So this is what I have noticed first. The next thing I have noticed is the angle turned from A to A dash. If you see, while it's going clockwise from A to A dash, the angle turned. It means this angle is smaller than the other angle from A to A dash. While it's moving, the angle is smaller. If it is rotating with constant angular velocity, then I will have a quick return over here also. Quick return, because the angle, see, if the speed is same, distance are different, speed is same, distance are different, so the longer one will take smaller time, or the smaller one, who will reach first? Who will reach first? Who is having less distance, right? So from A dash to A, while it is moving, it is moving faster, the slider is moving faster. But from A to A dash, the slider is moving slower, right? So now we want to know that quick return ratio. So while I'm saying from A to A dash, smaller one, we are always talking like it is alpha, right? So A to A dash, the smaller one, I'll say here it's alpha, and the remaining will be 2 pi minus alpha, right? 2 pi minus alpha. So I'm saying that this angle is alpha over here, right? Now, how do we find out this alpha? So that's a big question. So I can say that, see, I'm going to draw here in a smaller manner the complete picture. Yes, so this is what we can see there on top clearly. This is O, this is A dash, and I am asked to find out which angle, guys. I am asked to find out this angle because this is alpha. Now, how do I find out this angle? So I can see that the total angle over here is 360 degrees. A little observation can say that, sorry, 180 degrees from here to here. It's the same line, right? So total is 2 pi. So if I find out, if I say that, if I find out this angle which is on the top, let's say this angle is uh, phi. So if I say 2 pi minus phi is giving this angle, yes, alpha. Is it giving alpha 2 pi minus phi? Just pause for a moment and listen carefully, and sorry, pause for a moment and think. So 2 pi minus phi will give me alpha, yes. So alpha is equal to 2 pi minus phi. So this is the first statement I'm making. Fine. Now how do I find out this phi? Again, I'm drawing this diagram. Yes, this is something, and this is phi over here, phi, phi, and let's say that this is theta, and let's say that this is some angle. What angle should I give over here? We can give it gamma. Fine, gamma. Now in triangles we have a rule. In triangles we have a rule. The rule is external angle is equal to sum of internal angles. So opposite external angle, which is this one, gamma, is equal to sum of internal angles theta plus phi. Fine. This is a law and this is fundamental. Okay, this is a fundamental which we all should know. If you don't know, now you start knowing it. Okay, now you can also start knowing it, no problem. If you don't know earlier, now you learn it. Sum of external angle of a triangle is, sorry, external angle of a triangle is sum of internal angles which is on the opposite side. Okay, not attached to this side. So now from this, now how do I find out gamma? Gamma is very easy to find out, right? You have, see, this is gamma here. According to that down one, this is gamma. This is gamma. Now, gamma, how do I find out? I can find out by opposite by hypotenuse, right? Opposite is E and hypotenuse is L minus R. I can find out gamma, right? Yes. Is it difficult to find out gamma? No. Not at all difficult, right? Here you can say that gamma is what? Gamma is your E by cos. You can say gamma is what? Sine. If you can use sine theta, right? So sorry, sine gamma. So from sine gamma, I can write down. I'll just write down here. Okay. I hope that there is no problem. So sine gamma is equal to E by L minus R, right? Yes. And I can write even theta. Theta is this one, right? So where is theta, guys? So here theta. So this angle is theta. So here this angle is theta with respect to the stroke length. So this is theta here. So theta also can be written as E by L plus R, right? So sine theta is equal to E by L plus R. So you know now, sorry, L plus R. So you know theta, you know gamma. And what is phi? From here, if you see, what is phi? Phi is alpha plus 2 pi, right? Sorry. Yeah, 2 pi minus alpha. 2 pi minus alpha is phi. So phi, I already know, 2 pi minus alpha. Now substitute that in this equation, which you have already written. Substitute it. So you will get, finally, I'm writing it down with some other color so that visibility is good. I'm not going to change the page. Everything should be in a single page. It will look good. Okay, gamma is known already, is equal to theta is also known already. Sorry, yeah, plus 2 pi minus alpha. Now can we get alpha? Yes. Can we get alpha or not? So alpha, you know gamma from here, sine inverse E by L minus R. You know theta from here, sine inverse E by L minus R, right? You know 2 pi value also. Just put it, put alpha on the positive side and it will be like theta plus 2 pi minus gamma, right? Theta plus 2 pi minus gamma. So that is your final alpha. From here you will get the alpha and substitute the alpha, right? Again you have the same procedure, nothing to change. So it is okay, let's change the page. Sorry guys, just one moment. Change the page. So now what are you going to get here? Same thing, forward by return stroke is equal to 2 pi minus alpha by alpha, right? So forward is 2 pi minus alpha by alpha. So it's similar thing and you got the solution alpha you got from here. And now which is the forward? So I'm saying that this is the forward while it's going anti-clockwise, while sorry, while the crank is rotating clockwise. So forward stroke, because it's taking larger angle. See, this is the larger angle here, larger angle, smaller angle. Fine. So now I'll say that this is the forward and this is return. Now if you observe something, the whole story will change if you rotate it. If you rotate it anti-clock, sorry, yeah, sorry, this is anti-clockwise, guys. If you rotate it clockwise, the whole story will change. If it is going to rotate clockwise, what will happen? This won't be the forward stroke, it will be the return stroke, because it will take less time, right? See, the same thing will take less time if you are changing the direction of rotation. Just pause for a moment and think about it. Okay, I hope that you understood. You understood this is actually crank is rotating anti-clockwise. Let me write here clearly. Crank is anti-clockwise. Okay, here the direction is clearly shown, anti-clockwise. I sometimes maybe I said it clockwise, but the direction already I have shown here, anti-clockwise. Fine, it's actually anti-clockwise. Okay, guys, thank you. Hope you understood. This is also a quick return mechanism over here. Fine, even with offset slider crank chain, you'll have quick return mechanism. For any suggestions, kindly put it in comment box and share the video and subscribe the video for regular notifications. I'm actually covering the complete, planning to cover the complete theory of machines in the series of lectures. You have the playlist. You can, if you go through the playlist is arranged in such a manner that you can find each and every topic connected to the previous topic, and those are related and chapter wise you'll find. Actually, we are following a chapter wise. Even this will be useful for your gate exam and university exams. Okay, thank you. Please like if you like the video.